So our AI system is concerned with acoustic emotions, music generation, and emotional aware recommendations. We are 3 members, me, Wamani Joshua, and Aita Prince Joshua. Contents of the presentation. I'll take you through the first 7, that is the introduction, actually the first 6, that's the introduction, related work, problem statement, research questions and objectives, and finally the research contributions. So, a brief background and introduction of the system. It's developing an emotional aware music system for Uganda. We are bridging the gap between current music recommendation systems, which are limited in nature because they base on genre and artists to make recommendations, and yet music enthusiasts are able to connect with music on an emotional level. That is the reason why the system we are building aims to analyze and recommend emotionally music that is emotional. Yes, it is personalized to one's emotional state. So the system is a model that is trained on features extracted from a curated dataset, as we shall see, the dim dataset. It generates music based on the user emotional state, and it also recommends music similar to what a user feels like listening to. So there are other related works in the system that have already been worked upon by different universities, institutions, and individuals. There is the MAT, which is the music understanding model with large-scale self-supervised training. So this is a state-of-the-art system. It is self-supervised. It has self-supervised learning as well as supervised learning. It is a pre-trained system. The good thing about this system is that it is a teacher model that provides labels for unmasked for masked audio segments. It means that the system here can be used to train smaller distilled models. Then we have the Imogen system, which was created to reduce on human bias in annotated datasets. So this system, although trained on labeled data, is able to actually generate music that is unbiased emotionally. How does it do it? It has 2 stages. The first stage is to learn from a labeled or annotated dataset, and then after that it undergoes self-supervised learning, whereby it generates music from the music audio features. It means that it does not require any more data to be annotated on the music that it is able to work with. This works well for Ugandan music that is not annotated at all. So such a system would be very great. And this is our problem statement. The domain problem is that music enthusiasts relate with music on an emotional basis, but current music systems are not able to fulfill the needs of the listeners. So this is because there is limited emotional understanding. The systems currently rely on genre and artists, which are not enough. Then there's cultural bias and generalization. Most of the datasets that we have, even the one that our system is based upon, the DIM dataset is mostly filled with Western music. Then sparse emotion annotated data. Most of the music data available out there actually does not have annotations. These are labels to denote the emotion states that this music is able to invoke in a user. Then the computational problem is that such training of models, like the large acoustic models, requires state-of-the-art computers, which are power hungry. The training itself is compute intensive, and producing, generating music that invokes certain emotions in a user also takes time. There's a processing latency between when a user requests a certain music, a song, to when the system is able to deliver. And the cultural bias, which means that most music is uh, aligned towards Western music. So our system aims to solve these problems, as we shall see in the coming slides. So the research questions and objectives: we shall evaluate the the models that we'll be using based on various metrics, as we shall see. We shall use we shall evaluate it on accuracy. We shall use different metrics such as the mean absolute error and so on. We shall also identify the topmost important features that we can base on to determine the specific emotions of a song, and then we shall also determine the effective machine learning algorithms that we shall use. Our research contributions and outputs: we have in the system we have developed various models. We have trained 3 of them. We have the ridge regression, we have the SVR, that is the support vector regression model, then the XGBoost, that's the gradient boost model, and also the CNRR, that's the convolution recursive model, sorry, neural network. So we have also established some optimal features that we shall use for the model, because there are so many features that the dataset comes with, but not all of them will be necessary. So we picked the top most important and relevant features, scaled down the scale used in the dataset. It was a scale of 1 to 9, but on changing it to the circumplex model, which uses a scale of -1 to 1, the performance of the model was improved significantly by 42%. So at this point, I would let my group member take over to explain to you the methodologies and the system architecture. Thank you.
Good evening, everyone. My name is Omani Joshua. I'm going to be taking you through the methodology and our system architecture. So, our emotional prediction system follows a structured approach using acoustic feature extraction and machine learning. So, first we had to have the data set having the audio input, the features. So, after that, we carried out feature extraction, where our original dataset having 260 features were able to come down to 40, to reduce the complexity. Then we had a couple of models. We explored 3 models. One was a support vector model, which is support vector regression, then XGBoost. So we were able to create 4 models to support arousal and valence. So with that, we were able to compare both outputs and the outputs of both models, as we'll see the results in the later slides. We had the CRNN architecture. So this CRNN model was the one responsible for capturing the complex emotions in music. As you know, music isn't straightforward. So CRNN consists of 3 layers. That's the CNN, convolutional neural network, recurrent neural network, RNN, and the dense layer, which is for decision making. So this one, the CNN, is responsible for capturing the local features, the ones that change frequently and very fast with time. Then the recurrent neural network is used for checking the features that change temporarily over time. So the dense part is the one that are responsible for aggregating the learned features, then making the right prediction of valence arousal. So right here we have the optimizers and the callbacks and the loss functions. So loss functions are like they measure how long the model is predicted. The callbacks are used during training, in that if the model stops learning, a certain callback can stop the process or can do some specified action uh, following an action. So going on to the dataset description and EDA. So the DIM dataset obtained from the Computer Vision and Multimedia Laboratory, CVML. So it has 1,800 songs, 802 songs, and the uh, features are 260. So each of those songs has uh, corresponding arousal and valence labels. So the arousal and valence were the labels, while the features, the 260, were the ones we selected from the 40. So in front of you, you can see a heat map. So is a correlation between the features. So I selected a sample of 10, and this was used to choose the 40, because as you can see on the correlation graph, the red ones show high correlation. So most of the features that had high correlation were removed, were dropped and were dropped over the others, because that would bring in redundancy, and because they would literally be doing the same thing. So some of them were dropped, and yes, others were left in. That's why the biggest part is blue. Then this line graph is a sample chosen from the selected features, and it's root mean square energy with a time. So it shows how the energy uh, changes within the song over time, and this can be a good feature for arousal. So this dataset was clean, and it had no null values, it had no empty rows. Yeah, so below here are descriptive statistics that we were able to get from the dataset. So I'll call on Aita to take you through the next step of exploring the results from the SVR and XGBoost and other things.
The challenge was to use the features and annotations to train models that could be able to understand the relationship between the valence arousal coordinates and the features of the song. So we used the support vector regression model, an XGBoost, which is extreme gradient boosting model, and also a ridge regression model. We came up with interesting results. What you're seeing before you are some graphs of valence for predicted valence against actual valence and predicted valence against actual. So we tested for the ridge regression model. It actually performed the list, and so we decided to consider like the SVR and XGBoost. As you can see here, we created an ensemble model that combines the XGBoost and SVR. SVR performed well in predicting arousal. This is because SVR captures the like using it uses Kano method. It captures more like it's not like very linear. It captures more nuanced relationships than the linear regression model, than the ridge regression model. And so it was able to map and understand that certain features actually meant that the song is either hyper or slow. And that's very easy to map because like the features are very telling. It's hard for uh, a model to tell that this feature actually makes me feel happy or sad. That's balance. But it can be easy to tell how how aroused you are by it, whether it makes you feel excited or it makes you feel kind of depressed. So it was good at that because there's a direct relationship between the two, arousal and the features. It's almost very obvious. If I have upbeat music with a lot of noise, obviously there's going to be high arousal. So SVG was good at predicting arousal, whereas XG boost was good at predicting valence because the way it does it, it uses a simple decision tree models to kind of show. So it basically it's good at evaluating more complex relationships because that's how I found balance. Like it's more complex. So here are some of the results showing the actual valence versus the predicted value of the valence and error. The actual result with this ensemble model. So ensemble model just consists of the XG boost for valence and SVR for the arousal. Here are some of the data points on the arousal valence scale. So the black dots are real points, like from real songs, evaluated by real listeners. Whereas the blue and the purple and pink are for the different predictions by the different models. You may notice that there are not much outliers. So someone may argue that since like we're having a lot of predictions around the center, someone may argue that we may have overfitted this model because we're not accounting for these ones that are outliers. Like now, none of these outliers here has been like predicted correctly. Like the error margin is too high, and this could be trying to predict this. So like eventually overfitted, and we also learned that these models actually are just seeing a specific point in time of the song, not the entire picture. It's kind of like how you're watching a movie and you just see one frame. You're going to infer out of from one frame, but you're not going to know the relationship between the different parts of the movie, like the different pictures of the movie. So that's basically they were limited by their context. They couldn't see beyond the current frame. So understanding it from around was in itself a problem. And so that's why as you can see, the scores for R squared were very low. Some even failed to make it to zero point 0.5. So these weren't like the best. We opted for CRNN. CRNN kind of is much better because it's uh it's better at like evaluating more complex relationships, which is music. Music is not linear. It's more nuanced. There are a lot of relationships. For example, it kind of has memory. The I was able to see the full movie. So as we flow through the entire song, this model is able to understand when a beat drops. For example, a beat drops ta 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 ta, then you get to that drop. This model will be able to understand, and the other previous ones will just hear maybe low sound, then they'll say this is sad. Then when the beat drops, they'll say, oh, this is exciting, but they won't understand like those structures in music. This model is good at understanding. So it's optimal for audio processing within its convolutional network component, extracting audio features, as I explained before. And we're planning on using this model to find out the important features to focus on that help express the emotions. I like to have this as a mobile app. Basically, it could use Spotify API and like that will be very compute intensive because ranking each song on the valence-arousal scale will be hard. So we just have a simple mobile app. You feed in a song, it tells you its valence and arousal. So that's basically it. We hope to accomplish this task. We faced a bit of limitations with training. There are a few songs, and we also want to use folk songs. The challenge is we want to first create like a parent model based on all songs. We understand the important features and then use it to distill a child model that focuses on our local songs here, for example, in Uganda. So that's basically our plan. We were using static annotations, but now we're going to use more dynamic annotations over time with a CRNN model. Thank you for watching.